Hello everyone, it's December the 14th and we're ready to do the daily challenge for the 15th. Well, I'm in a crunch. It's the end of the semester. I have a report due in 2 days and I have a committee meeting in 2 days. So both are kind of collide with each other. So tonight, and after doing this, I have to keep writing the report. And tomorrow, hopefully I can. Yeah, I don't think I can finish the report by the end of today, so I have to spend some time tomorrow morning to finish it. And once I finish it, the remaining time I have to prepare for the committee meeting. So it's gonna be a little bit crunch, but things always work out because when the crunch comes, the efficiency goes through the roof. All right, let's take a look at what we have today. So the first thing is insert sort list. I mean, we've done this before. Are we sorting it? Okay. What are we doing? So given the head of a single linked list, sort the list using insertion sort. Return the sorted list head. The step of insertion sort. Insertion sort iterates consuming one input element at each repetition and growing a sorted output list. At each iteration, insertion sort removes one element from the input data, finds the location it belongs within the sorted list, and insert it there. It repeats until no input elements remain. Okay, so I think we know what insertion sort is. So what is given? Given is a head. Okay, so is there a requirement to do it in place? No, so we can build a new list. So basically, we're going to just read one by one every time we read, and then we can insert. Right? That's basically what it is. Okay, let's get this done as fast as we can, and we'll solve the other one. The other one I think will be more difficult than this one. We're entering the territory, I think, of medium questions that's not really easy. I mean, all these medium questions, like 100, 200, they are, I mean, let's be honest, they are not really medium compared to the like 300 or above, right? So these questions are low key, right? Low key, like borderline easy questions. But go to the 300, late 300 are the ones I'm actually handling right now. Some of them are not easy, right? I got stuck on these medium questions. Alrighty, let's take a look what we have. Alright, so what type of strategy do we want to use? Well, we're just going to read it one by one, right? So node equals head, right? And we just read node all the way to the end. And we want to create a new node, right? So res equals, I don't think the res could be a dummy. Dummy equals list node, right? And then head equals dummy, all right? Well, every time I'm gonna start from dummy, okay? So I'm gonna search, and once we find a position, okay, so what type of position are we talking about? We need to find a position that is the first one, because it's all sorted, right? So we find the first one. If I'm bigger than you, I keep going. So I find the first one that is smaller than me, and that's where I insert. Which means if you find the first one that's smaller than me, right? Because that's the limit. I cannot find the one that's bigger than me because I don't know. So I have to keep going. Which means I need, oh my god, it's actually not that straightforward, right? So for a node we set to dummy, right, and we are always looking for dot next, right? Dot next. Okay, while node. All right, so we have a node dot value, and then we're gonna say, what's that node? Second node. Oh, stupid name. Second node. Sorted. Sort node. Okay, Sn. Let's call it Sn. Sn equals dummy. It always starts with dummy. And then we say while Sn dot next. All right, while Sn dot next. If Sn dot next dot val is larger, not larger equal to, that's fine, larger equal to no dot val, then we break. All right, so then we break. Otherwise, we say Sn equal to Sn dot next. Okay, so we go through, we break out. When we break out, the Sn dot next is a none, or Sn dot next. So we need to insert the current node into, right, into the node between Sn and Sn dot next. How do we insert that? Well, we can just say, we can just grab it. No, I'll make a copy. It'll be easier. So Sn dot next shall equal to a list node. Val equals no dot val. Next equal to Sn dot next. Right? So Sn dot next, you can just, I insert a node there. Once I inserted it, so we're done with this one. So node equals node dot next. And once we're done, we're going to return dummy dot next. Okay. I feel like this shall be it. Okay. Give this a shot. Code. Yep. That sounds right. Let's test some edge cases. All right, so one value and 2, 2, 2, 2, 2, 2, 2, 1, something like that. Yep. Yeah, that should be right. I'm pretty sure what this 44 milliseconds is. It's just, I think, copied it. Right? I think this probably copy. I don't know. Okay, let's take a look at this one. All right, and take a look at this one. This could be like, I could be like, I think I copy the entire thing into a list, I sort it, and I put it back in. It could be what this one is. This might be the same as what I'm doing right now. There's another possibility that, because this one I'm creating a new list, right? It can also do with, if you want to do this, you can swap values, right? You can swap values, so you can avoid doing this. So you go straight from the second one, and then then you're gonna keep swapping, all right? If you're in a certain sort, you're gonna keep swapping. I don't know, what did I do in the past? This is insertion sort. We have a dummy. Then we have a tail. Current equals tail.next. Tail.next. Cut current out of the list. Ooh, I do not create a new one. I do cut it out. I cut it out. I mean, we can try to do that. It's fine, actually. Okay, let's try to cut it out. What is this one? I think it's cheating. Yeah. Yeah, this is cheating. Alright, so I want to cut it out, which I just think we can do. Right? So we have node. Well, if we cut it out, we can just go with head. Right? And then, so the next will equal to node. Right? So this one just equal to node. And oh, hold on. We need a few things, because if I do this, I need to. Okay. Hold on. All right. So we need to do a couple of things. Temp equals node. Okay. Node equals node.next. So we set the node, and then s.next equals temp, and temp.next equals sn.next. So if we do this, and we don't use node, we use head. See what's going to happen. I mean, what can you also do this? Head, temp, right? Because head. So we get a temp out, and I would actually say this is we're cutting. Say we cut, right? We cut the node from original list to new list. All right, let's try it. Who knows? I think this should be right. Run this. And this is, yeah, correct. And I think this one might be faster. $140 something, I forgot. Ah, it's faster. 140 something. So it is insertion sort that cuts each node from the original list and insert into the new list. O(n) squared, because it's insertion sort, it'll always be O(n) squared. And the runtime we hit is 1,652. There's an 52%, ranking. Oh, not bad. Not bad. All right, so we're done with this. 147, yeah. 147. That's a good number. 147 is a good number. Is the maximum break in snooker. All right, this is the real one, the real deal. Find k pairs with smallest sums. We're given two integers arrays, nums1 and nums2, sorting ascending order, and integer k. Define a pair uv, which consists of one element from the first array and one element from the second array. Return the k pairs with the smallest sum. So how many pairs we can have? Multiply together, that's the total pair, 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Ooh, Jesus. 10 to the 5th. 10 to the 5th. Okay. So we want to find the first k pairs that have the smallest. Okay. Well, the thing I can think about is probably q, because if we have this whole thing and we just pop, right? Maybe. I'm just currently I'm thinking out loud. Well, there are a lot of things that's already set up, like the information, right? Information, we already have information as these are sorted, right? So this feels to me it's a merging. Yeah, this is merging two sorted lists, right? So we know the smallest must be the first one, so they'll be popped, right? Oh, hold on, it's not merging though, because you don't get rid of them. So like we got the smaller of the two, okay. The smaller of the two, so I pick it out, and this one, at the smallest here would definitely be the smallest. But this one at the second smallest, that's not necessarily the smallest. Then what do we do? Okay, we have 2 pointers. So what we start from this, and then after done, we move to the next. So what we know is this one plus this one will definitely be larger than this one plus this one. So we do this one small plus this, 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 this. That we can push all these things into. No, that don't feel right. That doesn't feel right. I need to find the smallest combination out every single time. How do we find the smallest combination out? We have the first combination, Now we want to find the second combination. So the second combination, it could be this and this and this and this. But is that true? They have sorted values, right? The sorted values, A1, A2, A3, and B1, B2, B3, right? So the smallest is A1 plus A1 plus B1. That is the smallest. After that, we have 2 pointers, right? So after that, we can move the pointer to here. So I have these. So we know this is larger than this, but this is smaller than this. And this plus this. So the next comparison should be these two and these two. So we compare them and then we push the smallest in. Okay, so I can handle two situations. Now, two situations is done. Depends on where. Let's say if we put these two in. What's the next one? Well, the next one Hmm. Okay, the smallest value. So this is the smallest. We add everything. They will definitely be smaller than this one, add everything. Right? And this is the smallest. Add this thing. It will definitely be smaller than everything. This one, add everything. So what we can say, well, actually it's not smaller. The smaller are equal to. We don't know. Huh. The thing is, if I find the first pair, how do I know where to find the second pair? It's a good question. It's a very good question. We pick the smallest value, okay? And then we have all different combinations. So we can see to my right, if my right is larger than me, then me with all the value will be all bigger than all the other combinations, right? So these are all the smallest values, all right? Okay. Then I look to the other side. We have a smallest value as well. So that value, right? And then we also look to the right. Let me say if the right is bigger than me, then this value with everything would also be bigger or smaller than everything all the others would have. So immediately, if I have a situation where where the first value is smaller than the second value, the first value is smaller than the second value, then we immediately have the smallest must be this and everything, and this and everything, right? Well, I mean, and then one of the pair double counted. So that would be the first, well, I don't know, like num1, m plus n, right? M plus n minus 1. So the first m plus n minus 1 can be found immediately. Immediately. So depending on the size of these two, so we can analyze, right? We can analyze. And but we don't know which one is a bigger. We just know that they do contain the first. So we're going to put all of them in, push all of them in. Let me think. So, given the current situation, we have the starting position, right? We have the smallest on the first and the smallest on the second. But actually, no, we want the smallest value. So we find the smallest value among the two, right? And that can give us a bunch of values. And then we need to find the second smallest. Okay, so we find the second smallest. Doesn't matter where they are, right? It doesn't matter where they are. Hold on, but could it be the third smallest? Hold on. The smallest, we have a bunch, right? And then we go to the second smallest. They also have a bunch. But I can't interact with that. That can be small. Let me think again. We have the smallest, and then the smallest, and the smallest on the first, and the smallest on the second. So that we can create the smallest value, right? So that's good. That's good. Then what? Then I say I'm gonna try to find the next smallest value. And the next smallest value can be the smallest on the first and the second smallest, right? Or the smallest on the second and the second smallest on the first. So we compare, and then we say, yeah, there were other things will all be bigger than them. So I say, oops, no good. All right, no good. So the first smallest is still smaller. So then after that, we move forward. So the first smallest with the third smallest on the second. Then we'll compare that with the second smallest. And then on the first. So we compare this, and then it's still small. So we just keep moving to the right. Okay, we'll keep moving to the right until we hit a point where the smallest of the second plus the second smallest on the first becomes smaller than the smallest on the first plus whatever value is on the second. Now we can push this in, and then we move to the right. Then we compare again. So basically my current strategy is, given these two arrays, right, we will lock in the smallest on the first, the smallest on the second, all right? And then we always, because k is equal to 1, so we always push the smallest out. And now we lock in, and we have 2 pointers. The first pointer is pointing to on the first, so we can call it I on the first array, and then j on the second array, right? And then we just compare the first value on the first plus j on the second one, and the first value on the second plus I on the first one, and we compare which one's bigger, because these two will produce the next smallest value. They are the only ones that can produce the next smallest, because if there's anyone else, we can find smaller. So they just gonna check which one is smaller, the smaller, and push in and move blah, 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 until one of the pointer is exhausted. If that pointer is exhausted, basically what we're saying is, if that is exhausted, then what we're saying is everything is smaller than this. So then we move that forward, right? We move that forward, and then we return back to the front. and we try it again. And that actually going to be equal to, wait, hold on. No, we already fit everything. So if we move forward, then our starting point will also be forward, because this has already, it's still scanning everything, right? So everybody will start pointing to exactly the one but beneath us. Okay, so A start and B start. A start pointing directly down, and B start pointing directly up. No, we don't point up, because it's already done. So it depends, right? Hold on. I think we're almost there. We're almost there. It's just a transition period. The transition needs to be thought out. So one is done, right? Now we're gonna move it forward. Now as I move it forward, right? So one is done, the other is not done. So the other is still here. So once we move forward, I don't want to start at the beginning, because at the beginning we already done, right? So I want to move to the first one that the current is not pointing at. So the current is onto the right. So that's when we start. And then if this is done, now we're going to move to, okay, we're going to move to where? Move forward, right? We'll also move forward. And after move forward, we're pointing to the one that's not pointing at. So because everything else will have already scanned. Okay, let's try this. I have the idea now. So it's gonna be multiple pointers. So 4. We're talking about 4 pointers in this solution. All right, let's try this. So the ideal is we're gonna have 4 pointers. We're gonna write it well. How do we write? So we're gonna have I left, I right. Yes, I left and I right. I left, I right. Oof. I left, I right. J left, J right. Right. So I'm going to arbitrarily choose I left is going to be 0. I right is going to be 1. J left is going to be 0. And then J right is going to be 1. This is the starting point. And of course, the starting point we have res equal to, it doesn't matter, right? The pair. It doesn't matter. U comes from the first. So this is going to nums 1, 0, nums 2, 0. So that's the first one, right? Now, while k, right? So we do this, and then k minus equal 1. So now while k, and blah, blah, blah. Once we're done, we're going to return res. Okay. So while k, I'm going to do the next round. How do we do the next round? Actually, we cannot do while k. We can just say for this in range k minus 1. Yeah, probably easier to handle. So now what do we do? Now we're gonna compare, right? We're gonna compare. Compare what? Compare if nums1 I left plus nums2 j right, if that is, what if it's equal? It doesn't matter. Small or equal to nums1, nums2 j left plus nums1 I right. If that is the case, right? If that is the case, then we say res.append these two, right? Nums1, this. Else, res.append these two. So I right, j left. Okay? Now, the magic is here. If I left plus j right is smaller, then we're gonna move j right to the right. So we're gonna say jr plus equal to 1. Right? Now after jr plus equal to 1, then we're gonna check. We're gonna say if jr becomes equal to len num2. So we need mn equals len nums1 and len nums2. Right? So if this is equal to n, so we evaluate, then what we're gonna do is il gonna be plus equal to 1, right? Il be plus equal to 1, and jr will equal to, that is crucial, jr will equal to j left plus 1. That's what we rotate. Same thing here, but slightly different. So if ir, and then j left plus ir, right? And then ir plus equal to 1. And I say if ir is equal to m, then jl plus equal to 1, right? And ir will equal to I left plus 1. And then we go back. Then we do it again, right? Then we turn res. All right, let's try this. First one, oh, this. Right. It's the solution. This is the solution. Second one. That is the solution. 1, 1, 1, 1 is the solution. Last one. I can just write it 1, 2. That's 2. So 1, 3, 2, 3. Right? 1, 3, 2, 3. Oh, k equals 3. So that should be the minimum of k this and m times n minus 1. So make sure that they will not like index out of range. That's what I'm worried about. Okay, this is k smallest, nums1, nums2, k. Run it. Num1 is not defined because there's no num1, there's only nums1. Index out of range. Shoot. Hey, what the hell? This one's also not right. Oh, come on, man. Yeah, dummy. All right, I thought by doing this, I've already avoided it. Minimum m times n, right? M is 2, n is 1, m times 2, 2 minus 1 is 1, right? K minus 2, so 1. So we run this only for once. For once. And oh, JR is already out. Shoot, JR is already out. Okay, so we need to start at the beginning. How do we start at the beginning? Well, if we want to start at the beginning, everything shall be 0, right? Hold on. What we need to do is, this one's already out. To avoid this from happening, we can let me see. So basically we have 1, 3, right? And then once it's done and I have this and this, I don't have, right? I don't have. So we need to check. So we do this, and then I left and then J left are both pointing at here, and I right plus 1 and J right plus 1. So we need to check if I right and J right if they're in position. If they're not in position, then we definitely push the other one, right? So we have to do it here. We have to do it here. So what do we say? We say if JR, and then we just say if JR is equal to N, which means exhausted, JR has already been exhausted, then rest.append, there's only one possibility, all right? We're gonna append this, not JR, because JR is exhausted, so the only possibility is append this, append IR. Will both be at the end? I wouldn't think so. If both be at the end, that means we exhausted both of them. But if I exhaust, I always do this, right? And this just basically saying JL is exhausted. Okay, so the JR is exhausted. JR is at the end, right? JR is at the end after we have done this. Then we're gonna append this, right? And then what? If JR is this, we're gonna append this, and then, well, we append this because JR is exhausted, so I cannot do IL and JR, so the only thing I can do is IR and JL and IR, so we do IR plus equal to 1, right? We do IR plus equal to 1, and so basically, we shall say JR is exhausted, then we do this, right? And we basically have to do this as well, because after this, IR needs to move forward, right? That's when JR is exhausted. And what if IR is exhausted? I don't think IR will exhaust. Right? And say Aleph IR is exhausted. Then basically we're going to do this. Right? Now basically going to do this. Then Aleph. Now this Aleph is JR is not exhausted. IR is not exhausted. Then we do this. And otherwise we do this. Now they pass. But I feel iffy. Right? I feel really iffy. And these kind of, it's just repeated. Can we make them better? So if the JR is equal to N, or, right, because I'm basically doing the same thing as this one. So say, or let's say IR is smaller than M, and this condition, right, and this condition, well actually it's larger than, then we do this. Isn't that just else? Else, which means this and this, or I'm not sure, but I feel like yeah, it does pass. All right, let's give it a shot. Yeah, I don't have too much confidence, but let's give it a shot. Who knows? Maybe a pass. I got a wrong answer, so not too bad, but bad enough. Okay. Oh, problem. All right. Let's see. We have minus 10, minus 4, 0, 0, 6, 3, 5, 6, 7, 8, 100. Okay? So our scheme is JR is at the top. So I left, J left, IR, and JR. Okay? So we have minus 10, 3, that's in, that's for sure. And then we have minus 5, minus 10 plus 5, and 3 plus minus 4. So we say minus 10, 5. And then minus 10, 6, minus 10, 7, minus 10, 8, all the way to minus 10, 8. I should actually copy this. That's a good test case. That failed. Okay. All the way to minus 10, 8. And then the next one is minus 10, 100. Now, minus 10, 100 is way too big. So I explore 3 minus 4. Right? So now I do 3 minus 4. Ah, I see the problem. And then I just 3 minus 4. I do 0, 3. Ah, that's the problem. 3 minus 4. As I say, these are smaller, right? And these can be smaller than this. Yeah, so that's actually not right. We can keep going. Like if it's smaller, that's fine, right? If this is smaller, that's fine, and we can keep going until the point. Wait, why is this fine? Because this is definitely the smallest. And starting from here, the smallest is this, right? So if IL can keep getting smaller, smaller, right? Until it hits a value that is big. Now, when it hits a value that is big, what do we do? Is this smaller than everything else? No, that's not. Because we need to check this and this, right? And then hold up. Shouldn't we be looking for the two smallest value instead of picking one on the top, picking one on the bottom? Think about it. The reason that it doesn't work is because it did not pick two smallest value. If our anchor point is minus 10 and minus 4, the method shall work, right? So minus 10 will point into here, and minus 4 will also point into here, right? So both point into the same position. And then, well, minus 10 will go first. But the whole thing is minus 10 plus everything, right? Will be smaller than minus 4 plus the same value, right? But we cannot guarantee that minus 4 plus will always be bigger, because minus 4 can plus those small values and it can get, yeah, that's exactly the case. So, in this case, we have the smallest value, then we need to find the second smallest value. Okay, the second smallest value. So those are anchor points, right? So now we have anchor point, anchor 1 and anchor 2. And based on where anchor points are, so the anchor points can be on the top, on the same side, or on different sides. Right, so this basically is just a special case where the anchor points are on two different sides. If the anchor points are on two different sides, then it is guaranteed that this one will work. But the anchor points can change, right? The anchor points can change. If the anchor points are on the same side, then, right, then the new anchor point will point into something below that has not been hit before. Yeah, because that anchor point has not been done before. Okay, so now what? Now what? Yeah, now the complexity goes up. So setting 2, right? So when we start, we need to pick the anchor points. Basically, we need to find the smallest 2 values. All right, so it could be anchor point. One anchor point will be one of the list, and the other anchor point could be actually the other value. It could be the other value. Let's say we have the 2 anchor points. Then what? And then blah blah blah, and then this one, and then this one will blah blah blah. -4, -6, right? No, that still doesn't solve the problem because I got stuck on the first one. How do I know that one like it's a lost cause? I don't know. I mean, like threshold? Hmm. And what am I comparing to? Okay. Hold on. So we keep going, keep going, keep going. Once we find something that is bigger, if it's bigger than what we have currently. All right, hold on. It is correct, right? What we have. No, it's not. Not correct. We need to find the anchor points, and the anchor points can be on the same side or can be on a different side, right? So if they're on a different side, then it's right. We just shooting on both sides and try to find because that's the smallest one, right? That's the smallest 2. Okay, the smallest and the second smallest. So basically, we say the smallest add everything, the second smallest check on everything, and then the second small. So once one is n, so that one, let's say, is bigger than this, right? Then we start with adding this, right? So if it's bigger, shouldn't we like move forward? I don't know, move forward. Yeah. If something is bigger, hold on, let me think again. So once I find some pair is bigger than the other pair, then it's a lost cause keep going down. because we're just going to go from the other pair. So if it's bigger, then we just discard and we rearrange. And so push this one to this, right? And then pointing down. This one should be here. Now it's become this. So I say when this is bigger, now we move this one here, and now we're pointing down. Now we do this and this comparison. So this one is smaller, so we go this, and now we will move here, right? We move here. Now once we move here, now we find out this is 3, this is 1, so this is smaller, so we start doing this. But do we move? If we move, we won't be able to get it. How would you move then? Now you can't. You cannot move. Or we can push that into the priority queue. We push that into the priority queue, then we move. Okay. So now 3, 0 is too big, so I push 3, 0 into the priority queue, and then I will move myself. So I move myself to here. So now I'm staying at 5, 0. And I'm at minus 4, 5. So we do minus 4, 5, right? Minus 4, 6. Then I'm at minus 4, 7. Minus 4, 6. But we don't do minus 4, 7 because 0, 3 is, that's actually the same. I guess they just prioritize, okay. Now we check the top of the queue is smaller, so we get back here, okay. We get back here, so we do this, right? And after do this, which means after a streak of the smaller side, we hit a point. Because this is too big, right? If this is too big, we just push in and we try a new one. And new one is no good, so we keep going until we find a smaller one. It's actually back to the smallest. So we push it back. And then we keep going. And now we're in 3, 6. 3, 6 is too big. So we push 3, 6 in. And then we move again. So 3, 6 in, so we move again to this and point into 0. Because this one is pointing to minus 4. So this and this. The next possible. Right? Because we don't do all the others have done already. Okay? So this and this. Now we add minus 4, 7. So minus 4, 7 is too small than minus 4, 7. Right? And then now we can compare minus 4, 8. That's still smaller. And then minus 4, 100. That's too big. Now, when that's too big, we push this into the queue, and then move forward 0, and then 0 and 6. Now we have 0 and 6. Now we compare 5, 0, and then 6, 6, 0. 5, 0 in, right? And 5, 0 again in. 5, 6, too big. Move on to 6, right? 6, 6, and 0. Now just equal. Doesn't matter. We push 6 and 0. Maybe that's the one. Hold on.
Oh.
This is a little bit half-baked idea, but I'm gonna try. So in this case, we need to have this complex logic, right? So what we have, there's no anchor point. No, we pick a point on the top. So it's the same. I left and J left, right? Now, how do we handle? Oof. We should have to handle if it's equal to z equal to n. Right? If one of them exhausts, and the idea is one of them if it exhausts, that's the rule of exhausts, right? So we can do this. Oh, we have two sets of rules going on here. But in that case, we can actually push a dummy value into it. I can push an infinite value. Okay, we push an infinite value, then we'll always have I right and j right. All right. So now we have an infinite value. So now we're going to compare and compare. Okay, so which one is smaller? So the smaller one will go inside, but the big one is not going to stay there. The big one, we're going to push the bigger value into a priority queue, right? We're going to push that into a priority queue. And after that, the big one, we're going to readjust, right? Because I say this current arrangement is too big, right? We need to find something smaller. And something smaller to move me forward and move this. Because actually, I think it actually makes sense. So we need a heap queue, all right? Rest is this is this. For math, nums1 dot append math dot inf nums2 dot append math dot inf. Then we don't have to check. All we need to do is do this. If actually, this is actually, I think it's just going to be k minus 1, all right? Oh, actually, no. I do this. So nums, we're going to do the comparison, right? But we need to do actually two things. So we're going to compare, definitely. I'll compare first. We say I left and then JR is larger than JL and I left, right? So in that case, what we do not immediately push this, we do two things. First, we need to push this value into the heap. So we need a heap. All right. So we're going to say heap q dot heap push heap. So what are we going to push? So we push these values. So if this is larger, then we push the values first, right? So we push the value, and I left JR and the indices, right? We need the indices. Okay. So I'm going to push this value in. Meanwhile, I need to decide whether I want to append IR and JL. How do I know that? When I check the top of the heap, right? So we're going to say if this thing is smaller, what's a smaller equal to or smaller? Well, heap means that something occurs earlier than what I have right now, right? It's something in the heap. So if it's equal to, we will definitely use the heap. Okay. In this case, that's going to be smaller. Heap 0, 0 on top. If it's smaller, then no question, we are going to append the current smaller value, right? And after append, IR will plus, this is just the same thing, right? The same thing, IR will plus 1, and we actually will not need this. We don't need this, just IR plus equal to 1, because we can always push into the heap. Okay, so that's that. Now, after I push into the heap, we need to make changes, right? So IL and JR, they push into the heap. So now they need to change. How do we change? So I say IL need to plus equal 1, all right? And then JR needs to equal to the current JL plus 1. All right, so I'm going to make this change. And then, so that change, I do this change, right? And then I make the comparison of current JL and IR and see if that is smaller than a heap. Now, it is smaller than a heap. Then, we don't do anything about a heap. We do this, and actually, we do this. Else, if the heap is smaller, then we're gonna pop it out. We're gonna say underscore ILJR equals heap q dot heap pop heap. So we're gonna pop it up. So that one is smaller. So pop up ILJR. So once we pop up, we're gonna go back up, right? We're gonna go back up, and in that case, we did not move forward. So actually, a better way is while len res is smaller than k. That's the best way. If len res is smaller than k, so every time we add k, we add 1 until we add it and it come up, now we get out. So otherwise we do this and then we let the loop go back up. So now we have the new IR and the JR, and they are actually smaller or equal to this thing. So if it's smaller, we're going to go to the second one, all right? So that's that. Okay. Second one, else. So this is smaller or equal to this. Now we are going to heap push. Heap push heap. We're going to do this thing. We actually don't like it. I like it to be, let's do this. Nums2 JL, right? So they're always nums1 first, nums2 second. So we're going to do this. And IR JL, all right? That just means this one's too big, so I pushed in. And then, again, we're going to check. Check what? If this thing, because this thing currently is smaller, right? So if this thing is smaller than heap, 0, 0, then we're going to append this thing, sure. And after append, this is IR, IL, and JR. So JR plus equal to 1, right? And because I pushed IR and JL into the heap, so JL, IR, I pushed that into the heap. So JL need to be plus equal to 1, and IR needs to be IL plus 1. Else, that's when the top of the heap is bigger. So top of the heap is bigger, then we're gonna pop it out, right? Pop it out. Holy guacamole, the top of the heap. How can you be sure the top of the heap is the top of the heap could be on the same side. Are you telling me it doesn't matter? Hold on. Let me think again. What we're saying is IL and the JR is smaller, so I push this in, right? That's fine. Now we say IL is larger than the top of the heap. If this is larger than top of the heap, but the way we do it, right? The way we do it, it is, I should not say it's guaranteed. It's actually not guaranteed. Nothing is guaranteed. Come on. So this is smaller than the top of the heap. So the top of the heap can be on the same side. Like literally it can be on the same side. But does it matter? It actually does matter, I think. Hold on. I mean, Jesus. Top of the heap. If the top of the heap is on the same side, what does that mean? I mean, I am on IL and then JR, right? And if something, I'm on IL and then JR, right? And if in the past I got pushed in, right? If in the past the same configuration got pushed in because too big, and now I am at a position such that I am smaller than this, and I am also, but I am bigger than what has been pushed inside. I mean, in that case, shouldn't we swap? Okay. But how do I know if it's on 1 or if it's on 2? Oh God. So when we push in, we need to notify if it's the first situation, it's IL JR or IR JL, right? There's two different scenarios, because when we pop out, you don't know, right? And if it pop out, the new configuration is on the same side, then you need to ditch the current side and adopt that side, right? And the could be that side is smaller, right? Because if you do that, then the left side will definitely be smaller. Yeah, it could not be larger. It cannot be, because if it's the same, I've just gone through all. It must be something in the past I pushed in, and then I swapped. I changed the current configuration, and So I need to push another thing. Okay. All right, let me think again. So IL JR is larger than IR JL. So JL IR, that configuration is JL IR configuration is smaller. IL JR is bigger. So IL JR is bigger, so I'm gonna push the in. I get a sum. We do need a sum. And I say this, I call this the configuration 1. How about that? This is the configuration 1. All right. And after that, I'm going to check if the current JL IR is, I like to rewrite this. Now, if IR plus JL is smaller, so IR plus JL, if that is smaller than the heap, then we add this. We don't worry about the heap, and we make changes to both. Otherwise, then we don't pop. But it depends, right? I'm going to say if heap 0, right? Heap 0, 1, 2, 3, 3. If that equals 1, right? That means we need to swap this. Else we need to swap the other one, right? That means IR and then JR, they are larger than this. And then we find out that it's actually IR and JL. It's actually IR and JL. So if it's IR and JL, so we need to swap to the new IR and JL. And the other one, we just ditch it. Like, it's fine. We don't care. We just ditch it. So that's that. So in this case, I'd say we're going to push in 2, right? And then these things are the same, but we need this else statement. Again, if this one is 1, right? Now we're going to change this, otherwise we'll change this. Okay? That seems to be the same. It's repetitive. Let's try. Nope. Too many to unpack. Need a new value. This one we don't need. It's already checked it. Where? 0, 1, 2, oh, yeah. What the hell? We had an infinite loop. Why? Hold on. Yep, this one hit infinite loop. Jesus. Okay, let's see. What do we have? We have one side we have 1, 2, other side we have 3. Alright? So we're gonna start from this and this, and then we add an inf. So I left, J left, IR, JR. The first round, line is smaller than K, nums, IL plus JR is larger than nums IR plus JL. So heap and a push IL plus JR, and we put IL, which is 0 and 1, infinite, and then that's belong to 1. Okay, so that push into the heap. Now after that, we're going to check if IR and JL are they smaller than heap, the top of the heap, the 0, yes. So res dot append and now res equals 2. Oh, we want 3. All right, so res len equals minimum k and m times n. So res len. Okay. All good. Nope. Okay, fine. All right, for this, what do we need? Well, we can print res, right? And print IL, IR, no, ILJR. Let's put that also in the tuple. And JLIR. Okay, so we stuck at the -4 and 3. Okay, now they're both at 1 and 1. That is bonkers. How? All right, so -8, right? So now minus 100. So that is no good. So that should push into the heap, right? And then once we push into the heap, I want to check. And then this shall be smaller, right? And then rest of pen. So IR so I append -4 3. So IR plus equal 1. So IR shall equal to 0. Yep. So 0 IR is 0. So 0, 1, 2, 3, 4, 5. And then the other is 4, 1. 0, 1, 2, 3, 4, 1. Wait, hold on. Wait, what? Uh-huh. 0, 0, 0, 1, 1, then 0, 2. Yeah. And then 0, 3. Wait, hold a second. Why does this one change? Oh, because I constantly push it in. Oh. Yep, yeah, I see. I constantly push it in. That's the problem. So I say this one is smaller, so I already push this one in. push this one in, and I say I'm gonna go try my luck, right? So I try my luck, I go this one and this one. But if this is too big, so this is small, so this is too big, right? If this is too big, then I want to push it in and try to see if I have more luck. So I go up here, and it's still too big. So every time I keep going, right? 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 0, 1, 2, 3, 4. What about 4, 1? And now I'm on 4, 1. And then what happened? 4, 4, 1. So we'll have 0, 5. Right, 0, 5, and 4, 1. And 4, 1 is smaller. Right? 4, 1 is smaller. And I check the top of the heap. And top of the heap is smaller. So the next one becomes 0, 5 and 0, 1. Correct. That's how I designed it to be. So 0, 1. Now 0, 1 is smaller, so 0, 5 got pushed in. So now we can become 1, 1. Yeah, that's right. We're going to become 1, 1. And then we have 0, 1 and smaller, and then we go to 0, 2. All right? So at 0, 2, at 0, 2. 0, 2 is too big, so I push 0, 2 in. So I go to 1, 1, right? So it's too big. 0, 2 is too big. So I heap push 0 and then 2. Okay? So heap push IR and JL. I have to push in it. It's IL and JR is smaller, so we say, okay, this, the top of the heap, is smaller. So I shall append it. Now coming in is 1, 1 and 0, 2. And 0, 2 is 3. So that's 0, 2. So 1, 1 is smaller. So I'm going to push 0, 2 in. And then rest out append. Hold. I'm going to print the heap as well. Okay. And this heap looks wrong. I have a 90. Why is 90 pushed in again? That's the first question. The top of the heap is 1, 2. minus 4, 6. The value is 2. Alright, I have a couple of issues. One is the same thing got pushed in again. It happens after 0, 5. The first time I reach 0, 5, like 4, 1, I push 0, 5 in. Right? I push 0, 5 in. The first time 0, 5 is too big, right? 0, 5 is too big, so I push 0, 5 in, and I have the other one is 4, 1, right? So I push 0, 5 in, hit push, and then the top is this, so I got a new value. But once I got the new value, shouldn't I also change because I pushed in, right? I pushed in already. So if I pushed in already, this one shall change because I pushed in. By default, my value will change. If I change back, that's a different story. So I'll always change. Okay. Now what happened later? Well, what happened later is on a heap, I have so we're at 1, 1, and a 0. Okay, I'm gonna run this one again. Oh, I got index out of range. I went all the way to minus 5, minus 4, 5, minus 4, 6. Okay. Now, next one we should go to 0, 3. So where we at? We at then we go out of range. 6, 6, 3. 5, 2. 0, 1, 2, 3. Wait, how do we get a 5, 2? 0, 1, 2, 3, 4, 5. Oh, we do have 5. 5, 2. And then, oh, IL plus equal to 1. Huh. So I keep adding, then I keep going to the right. Why would I keep going to the right? It's 2, 1. Right? 2, 1, 0, 2. The next one becomes 3, 1. What? 2, 1. 0, 1, 2. Right? And then 2, 1. That's 3. And then 0, 2. 0, 0, 1, 2. Hold on. 2, 1. 0, 1, 2, 0, 1. So 2, 1 is this. And then 0, 2 is 0, 0, 1, 2. 0, 2 is this. And 0, 2 is smaller, right? 0, 2 is smaller. So I push 2, 1 into I don't see 2, 1. Oh, here. I push 2, 1 in. Okay. We push 2, 1 in, and after we push 2, 1 in, and then we say this one I will add. Because there's no point going here, so add. Then JR equals to 0, so it becomes 3, 1. Right? And that becomes 4, 2, and all the way. I see. And it just never pop out. Minus 4, 6. 5, 2 we already pushed in. And then we just keep moving forward. We can push it again. Yeah, we can push it again. And then if we push again, then try to wait for the turn, right? Yeah, we can do that. I mean, and we can also say if it's reaching the end, then we just don't push. That is also possible, right? If it's reaching the end, then we simply don't push. So we don't have infinite inside. So we can say if IL, because JR is JL plus 1. We say if IL, right, and JR, if IL equal to M, right, or JR equal to N, because that's why it's going to be bigger. But if anyone is bigger, so if I hit the end, I just stay there. Yeah, okay. So if let's say if this one is smaller and JR is smaller, so that means it's valid, then we do this. If they're already hitting the end, that means it's invalid. So we don't do it. We just keep them as is. And then the other things are the same. So here we'll do the same. We say if, now this one concerning IR smaller than M and J left smaller than M, then we do this. Okay, we did produce a result, but it's not correct. Okay, we did minus 4, 7 instead of 0, 3. I already said only this will append, otherwise will always pop. Okay, so what happened? So what happened is a -4 -6. Alright, so at a -4 -6, I have 5, 2 again, 5, 2 again, that's as expected. And then I have 5, 2, and 2, 2. Okay, 5, okay, I need to redo this. I changed some code. So I have 5, 2, and 2, 2. Okay, 5, 2. So 0, 0, 1, 2, 3, 4, 5, 0, 1, 2, 5, 2, and 2, 2, 0, 1, 0, 1, 2, 0, 1, 2. So it's actually pointing at 0, 6. And the top is 3. So 0, 1. There's no other 3 inside. And 1, 3, 0, 1, 0, 1, 2, 3. What? It's never entered it? Seems like it. Seems it just never entered it. But we have -4, 3, right? We added -4, 3. After that, we have 0, 1, 2. Have 2, 1. Then we have 2, 1. 0, 1, 2. Have 2, 1. And 2, 0. 0, 1, 2. 2, 0. So 2, 1, and 2, 0. Then what happened? I have 2, 1, 2, 0. And the top of the stack is a value 1. So I swapped out. 2, 0 become 1, 1. So anyway, 2, 0 is smaller, right? 2, 0 is smaller. And then, so 2, 0 is also not smaller. So that's why IR and JL gets swapped. So once it's swapped, the value it's currently pointing at is gone. It's current pointing at is gone. Well, I'm gonna call quits on this. Jeez. I need a hint. Yeah, how does this one work? It's like 1, 1, and 1, 2, but this is 1, 1 smaller, okay? And then 1, 2, and then 2, 1. About 2, 2, 1. And then 1, 2, and then 2, 2, and then 1, 3, and 1, 3, 2, 3. Oh, doesn't make any sense. I guess maybe it'll be fine if we do it that way. But anyway, this one's not right. I think what it is when we swap, the ones we're getting swapped shall also be going inside. Right, so this is the current smaller of the two, and the current smaller is still larger. And then this means we need to push again, like heap q dot heap push heap, again nums1 il plus nums2 jr il jr 1. So we're going to push and then we're going to change it. Same thing here. We're going to push irjl irjl, and this is 2. Man, this is just spaghetti code. We're gonna have very, very spaghetti code. Nope. Nope. Alright, I feel like this is not right. We're not on the right trajectory. And we are having tremendous issue. Probably because we have duplicates. We're stuck at 5, 2, and a 1, 3. Why are we stuck at 5, 2, and a 1, 3? We had 5, 2, 0, 1, 2, 3, 4, 5, 2, and then 0, 1, 0, 1, 2, 3, and a 1, 3. And then top of this is another 3. 2, 0, 0, 1, 2, 2, 0. So what? So 2, 0 will pop out, right? Because it's in this situation. 2, 0 will pop out. It belongs to 2. So 1, 3 will change, right? Basically, I'll push 1, 3 in and pop out. Oh. Yeah, it's not happening. Yep. Because I won't pop this one out. I'll only pop 1, 3 out. Because 1, 3 is a 1, as a 2. That's just ridiculous. I mean, maybe we can add yet another one to indicate that the smaller of the two. Okay? Oh, mamma mia. This is just ridiculous. Now, at this point, this is ridiculous. I'm just trying to see how much I can push on this one. until it doesn't work anymore. I think we're getting close. We're getting very, very close to me giving up. And I guess there's no point doing this. Like, what's the point? Alright, I'll say this is the last push I'm gonna do. And after this, I am going to see if there's any hints. And I'm going to work on that. I told you, these problems are not easy. Like, I don't know, I can't do them. For whatever reason, I can't. Alright, that's my last shot. What the heck is this? I have the same thing repeating and repeating. What? Alright, this is not right. Alright, let's see. Related topic. It is heap, but need to have a smarter way. Need to have a smart way to handle the heap. Yeah, we just throw out what we have. It is heap, but so my idea is we keep throwing pairs into the heap and make sure each pair we throw in is likely to be small. So we throw this, and then we throw this, or like each time we pop, right? Think about it. Each time we pop, we always pop the smallest pair. Each time we pop the smallest pair. Okay, and after we pop, we're going to keep adding new pairs. Now, when we add new pairs, we do it strategically, right? So we'll add, and then, but how will we guarantee that each time we add, it's always going to be the smallest? That's why I have we can pick the smallest among the two, and then pick the second smallest, right? And then the second smallest plus, like, I want to find the second smallest sum. Yeah, I shouldn't say the second smallest sum. Because we have the smallest value, right? If we have smallest value, no matter which side it is on, it can add. We just need to know how long it can continue. So we need the second smallest value. It can be either on top or either on bottom. Doesn't matter. If on top, then it's that. That's the threshold. If on the bottom, then that is the threshold. It's the same, right? The threshold is the same. Okay, so we have the threshold. So when the smallest, we keep adding until we cannot add any more, right? And so when we cannot add any more, I'll push this one into the heap. Okay, so that's actually recording this one into the heap. So now we're starting from here, right? And when we start from here, what is its threshold? Well, I mean, that's the anchor. Doesn't matter, whichever one is the smallest is going to be anchor. And now we're going to go all the way down. So what is the threshold for that? Well, the threshold for that is we need to find the third smallest value. All right. So what is the third smallest value? So currently it's here, right? So these two are of concern, and the third smallest value, it should be either this or this, right? Because the second smallest is the anchor, and the first smallest we cannot do anymore because that's already bigger, which can actually be an anchor as well, but we need to find the third smallest. So I have third smallest, doesn't matter, we find one, and then if it's here, no matter where, right? Because we're here, it's either this one or this one, all right? So if it's this one, then I'll add this. That's the third smallest. If it's this one, I cannot add this because we already done it. I can add this. Then that's the third smallest. No, I don't feel it's correct. All right, 2 hours. Let's give up. Ah, press the wrong button. One-liner. Okay, solution. Okay. The next minimum pair, I want to need to maintain k possible candidates. For every numbers in num1, its best partner always starts from num to 0. Since array are all sorted. Okay. And for a specific number in num1, its next candidate should be this specific number plus num2 current associate plus 1, unless out of bound. That is correct. How does solving work? Okay. And most k. So step 1, I'll push k into the heap. Yeah, it doesn't matter. We pick this and this and this, and put k into the heap, and then afterwards we pop out. That definitely be the smaller one. All right, and then the next round I go this to here. All right, but we don't. We check. Right, so we push, then we pop. Right. Can we guarantee this is small? So we push everything in. Basically, it's a nums2 with everything. And once it's done, the next possible smallest, it is this one and this. Right? This one and this. Then we pop this one, comes out. And then what? And then we do this. Because the next biggest is going to be 7 to 9. And 11 to 9 and 16 to 9. And now we move on to the next one. Hold on, let me think again. So we have everything on this, right? Push in. Okay. And then And the next step, we need to check. So we know 1 and 9 is the next possible smallest value. So we check, right? We check this with, so we push this into the heap, and now we pop the smallest. So we can guarantee that the smallest is inside the heap, so it'll pop out. And then after that, because everything associated with this is in, right? So now we say everything needs to be associated with this. This is in. So this is the next possible, right? Because this plus this is inside. So this plus this is smaller than any of the other things. So every time we push in is the smallest, is the current smallest value, right? Because 7 plus everything else will be bigger than 7 plus 9. So and then everything else plus 9 will be bigger than 7 plus 9, right? So the only possibility that a pair is smaller than 7 plus 9 will be everything plus 2, which is already in the heap, or everything here plus 9, which is already in the heap. Therefore, every time we do, it's going to be smallest. It makes sense. No, we're not close. We are not close on this one. Yeah, I was going to say I think we're close, but we're not. We are very, very far away. All right, so we don't need this. We probably don't need this. Well, actually, we can have this. All right, so let's recap. So what happens is we have nums1, nums2, right? And we say if we say nums2 is the anchor, then the first possible smallest is num2 with everything in nums1, right? So we push those into the heap, and then once we do that, pop one out, and that one is guaranteed to be the smallest, which is true. Next round. So the next round we need to push in a value that is the smallest. All right, that's the smallest. So we have the first on number 2 and everything, right? So we know that the next smallest value must be, remove the anchor on number 2, right? Remove the anchor because everything we're already done. So remove the anchor number 2, and then we go for the second value number 2 and the first value number 1. So that pair is smaller than any of the remaining pair. That is the key. It's smaller than any of the remaining pair. So we push whatever pairs into it, right? And then the new pair is smaller than any of the remaining pairs. No remaining pairs that's not in the heap is smaller than that, right? Because if we pick any of the other, that's bigger. If we pick any of the remaining, that's bigger. But the only possibility is we're going to move the second one to front, but we already pushed everything in the heap. So the current value is the smallest among the values that's not in the heap. So we push that in, right? And now we can pop one out. Once we've done that, we move top, go over here. Again, everything that has not pushed in the heap are bigger than what we have right now. That makes sense, huh? That makes sense. We don't need to do that. And basically, we only need on the j. Ji equals 0. That's all we need. M heap. These are all fine. Right? These are all fine. So what we're going to do, heap. Right? Heap. We need to add values to heap. Okay, how do we add values to heap? I'm going to say for I, that's a J, J left. Oh, that's just J. And for I in range, right, in range minimum, K and len nums 1. And then I'm going to push in this. What's this? Nums 1I plus nums 2, 0, right? And then what, the positions? Yeah, we can pop all the, it doesn't really matter the position, right? No, it does not matter the position. So we can just do nums 1I and nums 2, 0. So push everything to the heap, and heap q dot, we don't need the heap 5 because they're already sorted, right? So it's already sorted, and rest is this. Then rest always dot append. So we can actually do this. I can say dot append heap q dot heap pop, right? And 1, 0, 1. Right after do that, it's actually j going to equal to 1, right? So I'm going to say j is equal to 1. So I have to do that, and and I. So I, j will equal to 0 and 1, right? So this is how we do. So pop out, and then we're going to push ij into it. So heap q dot heap push heap nums 1 I plus nums 2 j, and then nums 1I nums 2 j, right? So we push this into the heap. After we push I plus equal 1, right? So just keep pushing, and if 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 I is equal to m, right? If I go to the end, I equal to 0, j plus equal 1. Heap pop. Heap q and heap pop. I'm going to put heap in it. Minus 4. Nope. Nope, that is not correct. What happened to 10, 6? No, that is not right. This is minus 10, 6 is not inside. So what I think is we need to find the smallest. The anchor has to be smallest. Yes? No, it's your program. The anchors doesn't have to be smallest. So in this case, I pick this as anchor, right? So we put boom, 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 all right? And a -10 to 5. And then we say -4 to 5. Then we are missing -10 to 7. Yeah, we are missing. So that analysis is not right. Oh my God. Yeah, I do all that. And then next one I say this plus this. This plus this is correct. But then this plus this, that is not correct. What if this one is small? What if this one is super small? Right? If this one is super small, then this one plus this can be smaller than this one plus this. Okay. Next could be, why did you only add ij plus 1? When ij is pulled from the priority queue, it is guaranteed that there is a pair I plus 1 x is in the queue. But the next one depends on what you pull out. I read again. For every number is in number 1, its best partner always starts from here. Since arrays are all sorted, and for a specific number in number 1, its next candidate should be the specific number plus num's current associated index plus 1. So we'll add everything into it, and then we pop this, right? And once we pop this, then the next possible, because I've done this, so everything on this associated with this is done. So the next possible must be from this plus this, right? So I push this one in, and I pop. So I pop this one out. Once I pop this one out, right? So whichever value I pop out, what we know is everything further down has already associated with this. So we need to push this and the next one. So that's why 7 and 9 push in. And next one is 110 pop out. No, next one 19 pop out. And after 19, I say, okay, the next possible, because everybody else plus 9, they have not been in yet. But why do I not do those? Why do I do 1 plus 10? Because I am standing in the perspective of 1. Right? I want to find, so every as they pop out,